We're going to continue on with section 3.3 here and talk about pulleys. The pulleys we're going to consider in this section are going to be frictionless and ideal. And what that means, we'll talk a little bit more what I guess ideal means in the future, but for now what we should understand is that all pulleys do is change the direction of the force. That means that the tension is going to be the same on both sides of the pulley. Alright, so let's just look at a couple pictures here. This guy has some force that he's pulling back on here with. The tension is going to be going up like that, and there's going to be another tension in this side of the pulley. Because that is a pulley, all it does is change the direction, and that means that the tension is equal to the tension, same tension on both sides of the pulley. If I have a mass that I'm pulling up with some force, let's just say that I have a weight equals mg. Actually, let's just take a little distraction to talk about what weight is. If you remember from physics or from high school, the weight on Earth is equal to mass times gravity on Earth. The weight is what we feel. Your mass is kind of a figure of that changes in different gravitational fields, and we don't really have too many gravitational changes here on Earth. But the mass would be the same regardless of where you go in the universe. However, your weight is going to depend on what your gravitational attraction is. The units in the English system are pounds, and the units in the SI system are newtons. Mass in the English system is units of slugs, and mass in SI units and metric system is kilograms. Gravity is going to be the acceleration of gravity, so 32.2 feet per second squared in the English system, 9.81 in the metric system. So if you need to review that, look at chapter 1 in our textbook, or some of your physics work from before, and review what is going on. Just a word on units and what am I trying to say? Just a word on units and significant number of significant digits in the gravity. When describing gravity, make sure that you use 32.2 feet per second squared and 9.81 meters per second squared. In other words, don't forget that extra, or that don't forget all three of your significant digits. Just a word on acceleration of gravity and other kinds of things. We want to make sure you use at least 3 significant digits, even in gravity. So make sure that the units are 32.2, or the numbers are 32.2 and 9.81. Just make sure you use all 3 significant digits when you're describing that. All right, back to our pulley problem a little bit. All right, so we have this weight coming down. That means that there's going to be a tension. Let me go back to black ink. There's going to be a tension in here. As it goes around the pulley, there's also going to be another tension, but we know that that's going to be the same. It's going to be equal to T1. Now, the force, because the force in that rope is going to be is the tension, we know that that is going to be equal to T1, but we also know that it is equal to mg. In other words, there's not going to be any change in the force as it goes around around that pulley. Let's look at a freely rolling pulley here. This is kind of a special case of pulley problems, but if the gravity is going straight down, or if the weight is going straight down like this, and it happens to be in the center of it doesn't even have to be in the center. It is, if the weight is going down and the pulley is freely rolling, meaning that it is at a stable condition, we do know that tension is going to be equal to the same tension on both sides. But here's kind of a clue. It means that the angle is also going to be the same on both sides. In other words, T1 is equal to T2, and theta equals theta. And those are kind of the rules of freely hanging or freely rolling pulleys. Alright, so we can find out what that tension is we're looking for. In fact, it even kind of gives you the clue when you look at the problem. It says there's a 5 kilogram block suspended by a pulley. Determine the force in the cord ABC. So it's telling you that there's no change in the tension as you go from A to B to C. All right, let's draw a free body diagram of the pulley and see what we can find. All right, so here I have a pulley, tension going this way, tension going this way. They are the same tension. There's a weight going down. This is going to be 5 times 9.81. There's an angle, theta, and those thetas are going to be the same on both sides. All right, let's draw the components of the forces. I know I have a T cos theta going this way and a T cos theta going this way. And then up in this direction, I have T sine theta on that side and T sine theta on this side. Again, just to remind you, so there's the X and Y coordinate system. All right, let's see if we can find the angle theta first of all. If we just look at our picture, it says that this makes a right triangle right there, where this is 0.15. That's 0.15. This distance, because it's right in the middle here, is equal to 0.2. So let's solve for that angle theta. Sometimes it'll be nice and easy like this, and sometimes not. But we should be able to say that the tangent of theta is equal to the side opposite over the side adjacent. So it would be 0.15 over 0.20. And theta is going to be equal then to 36.9 degrees. All right, that's kind of handy to do. All right, let's solve for the force if we can. Well, sum of the forces in the x is equal to 0. So I got minus t cos theta plus t cos theta equals 0. Now, what we'll find in freely rolling pulleys like this is the x equation generally doesn't give you anything. It says, you can't solve for t, even though there's only one unknown in that equation. There's no way you can solve for t. So let's move to the force in the y direction. Sum of the forces in the y is equal to 0. So I got minus 5 times 9.81 plus t sine theta plus t sine theta equals 0. And what you'll find is that freely rolling pulleys generally can be resolved. The forces can be resolved using the one equation, the force in the y equation. And I will often simplify it just because the t sine theta and the t sine theta are going to be equal to the same. I'm just going to say 5 9.81 plus 2t sine theta equals 0. And then once we know our theta, we can plug that in there, and you can solve for tension is equal to 40.9 newtons. Anyway, that's a quick analysis for many of the freely rolling pulleys, and solve for the angles if you can see them, then jump straight to the y equation. Most of the time you don't even have to use the x, some of the forces in the x equation to solve your problems. Well, I just want to point out a couple of things about knots versus pulleys. We already solved this problem, of course, and that's obvious that it is a pulley. You can kind of look at it. This particular one doesn't indicate, just by the picture anyway, you can't really tell whether it's a knot or a pulley. However, this problem, if it said it's a frictionless hook or something like that, then it basically acts the same as a pulley. Because pulleys are frictionless, there is no friction pushing back and forth. If you have a frictionless hook, then it acts the same as a pulley. All right, here's a couple of pictures of knots, which are maybe obvious, but the obvious look of a knot is that it's a ring or something like that where things are tied in there, and clearly it can't slip. It can't act like a pulley in any way. And often we will have combination problems. We'll have things that look like this, where maybe we'll have a pulley on this side and a knot here, and so just something to be that's obvious. But whatever this P is, that's going to be the same tension that is in there. So there's going to be on this side of the pulley, there's going to be a same P, and whatever tension there is in that rope is going to be P all the way over here. There's also going to be some tension over on that side, but if we draw a free body diagram of that knot, there's going to be an mg, is going to be that P, whatever that P is over there, and this tension on that side, and that's your analysis. You'll have two different angles here, theta 1 and theta 2, but you should be able to resolve that. This is an activity I'd like you to try, and what we've got here is this box. It happens to be empty right now, but it has some weight and is pulling down. It's being supported ultimately by that force going up, by that tension in that cord. If you were to isolate this whole box and or draw the free body diagram of the box, you could probably agree quickly that the force is going to be equal to the weight. However, what we're looking for is the tension in the cable. And there's two suspension, I guess, scenarios. You could suspend the cable this way, or you could suspend the cable this way between C, O, and D. And the objective is to try to find out what the tension is in these two configurations and which is greater, and try to understand why one might be greater than the other one. So pause the video while you work on this thing, and I will give you the solution in a minute. Well, here's the solution for these two configurations. Configuration 1 is when it's being suspended back this way. I guess first of all you have to find the angle. Understand that there's a force going up, the weight is going down. The angle here is going to be the same as the angle there. So either way works on that, but I found the internal angle there is equal to 48.3 degrees. And then if you draw the free body diagram, and we get this. Understand that those tensions are going to be the same. We got a cosine component going that way, 2t sine theta going that way, and you can solve for the tension. The other configuration is over here, and in this case the distance here is obviously less. We have a different angle, 70.5 degrees. Drawing a similar free body diagram, you can find that the tension is quite a bit less. So here's just a little bit of a takeaway here. Why is one so much higher than the other one? What we'll find is that the shallower the angle, or the smaller the angle, when you have a configuration like that, you'll get the highest tension. Let me just zoom out here a little bit. In this case, this has a smaller angle theta there, and so you're going to get higher tension when that happens. If this angle were to approach 0, in other words, you'd have a even smaller and smaller angle, then the tension would approach infinity. So on Earth you can't have a 0 angle. In other words, that theta 1 there, theta 1, could never be 0, because the tension in the cable would be would go to infinity. So don't look for a solution, I suppose, if you try to have a straight line on that tension. All right, well, I hope that works for you. Good luck with the homework.